You will let me know when to start. Oh, there's a message that says I can start. Okay, thank you very much. Well, my name is Awonke Nqayiya. Today we are doing probability, which is basically defined as an event over a number of outcomes, if you can see on the screen over there. So a probability is more like how likely an event, how likely is that an event will happen. For example, if you go to a bag of balls and there are like 10 balls in that bag, and then you are told that 6 of them are black and 4 of them are white. So when you go and take that one ball from that bag, how likely that the ball that you're going to take is black? Remember, there are 6 black balls and there are 4 white balls. So the probability that you take the black ball is basically the total number of the black balls divided by the total number of the balls in that bag, which gives you 6/10, which is, I think, is it 3/5? I think, yeah, that is 3/5. So the probability that you will take a black ball out of that bag is basically 3/5. So that is what we are going to be talking about today, and we will dive deep into other things such as the Venn diagram, the tree diagram, independency, mutual exclusive, and stuff like that. So we will dive deep into that. So let us begin. I think I want to begin by defining what we mean by events. I think you saw from the previous slide, we said that probability is an event over outcomes. So an event is an occurrence. Let's say with that example that I made, there is a box over there, and then you have yourself 10 balls that are there, and 6 of those balls, 6 of those balls are black, and then 4 of them are white. So an event is like an occurrence. When you go and take one ball out of that bag, and then that ball that you take it turns out to be a black ball. So that is an event. The ball that you have taken is black. That is the event that has occurred. So that is what we mean by events. It's like taking out a ball from that bag. Remember, from that bag, there are 6 black balls. And then there are 4 white balls. And then in total, there are 10 balls. So 6, there is the number of black balls, 4 is the number of white balls, then 10 is the number of balls that are in that bag. In statistics, well, in probability in your case, since you are in high school, we say that 10 is the sample space, which is, if we say, which is NS basically, which we write it in maths as NS is equal to 10, which is a sample space, the total number of options that we have. We have about 10 options, which means we have about 10 balls. So an event is like event A, taking out a black ball. So that's an event. Another event can be event B, whereby you go for the second time, you take another ball, and then the ball can be, let's say, white on the second event, or even on the first event, the moment you go and take that ball, it can be black or it can be white. So we will say A is the black ball that you take out, and then B is the white ball that you take out. So it becomes a white ball. So that A and B are what we call events. You go and take that one ball, it turns out to be black. Or you go and take that white, you go and take that ball, it turns out to be white, and that is event B. So event A, you take out the black ball. Event B, it turns out to be a white ball. Okay, I think I'm crossing these two words. You go and take out that one ball. When it turns out to be black, that means the event that occurred is event A. When that ball turns out to be white, the event that occurred is event B. So that is what we mean by A and B. So when you calculate the probability of A, it becomes the total number of black balls divided by the total number of balls that are there, which is a sample space. So that NA is the total number of white balls, or of black balls, I mean, that NA, because A relates to the black balls. So that will be basically 6 over 10. And then the probability that the ball that you take is not black, is actually white. It becomes the total number of the balls that are white divided by the total number of balls that are actually there in that box. And that gives you 4 over 10. You can further simplify your answers, or you cannot. That is actually up to you. The first one will tend to be 3 over 5. The second one will tend to be 2 over 5. So that is the very basic introduction about events. It's important that we start there so that we don't get confused when we grow into advanced material. So we will continue with this concept of, with this example, basically to go and discuss other things. There are other events besides event A and event B. Sometimes event A can occur at the same time with event B. Sometimes one will prefer that either event A or event B occurs, either one, whether A occurs or event B occurs. We also deal with those things in probability. So it's important that before we go and use them in more advanced examples, let us try and understand from the grassroots. So when we talk about event A and event B, or when we talk about event A or event B, it's like when someone goes and buy something for you in town. Let's say they go and buy a car for you. You give them an instruction that they should bring a car that is silver. in color, silver, okay. So that is the first event. You expect the car to be white. And then the second event, or the second condition that you have, you expect the car to be an Audi, for example. So when we talk about event probability, when we talk about event A or event B, we talk about a scenario whereby this person comes back now with a car. You are happy if the car is silver, or you are happy if the car is an Audi, and you are happy if the car is silver and an Audi. So if one of these two conditions or both are being met, then you are happy. If the car is silver, then you are happy, regardless of it's an Audi or what. If the car is an Audi and not silver, still you are happy. Either one of these two, if one of these two happen, then you are happy, you are sorted. That is what we mean about probability of A and probability of B. In a scenario whereby we talk about a Venn diagram, we will talk about a Venn diagram again, but I think it's important that I mention it here. If we have event A and event B, then a scenario whereby you are happy with whether event A or event B happens includes the entire subset of A. That means you are happy if the car is a silver car. Another thing, you are happy if the car is an Audi. So that is what we mean about probability of A and probability of A or probability of B. There's another condition that you might want to tie when you send this person to shopping for you. You will say, okay, I want a car. I want it to be an Audi, and I want it to be a silver car. So that's a very strict condition now. You are not willing to settle for a silver car, regardless of its Audi or what. You are not willing to settle for a silver car. You want it to be silver and at the same time to be an Audi. And you're not willing to settle for an Audi and let's say it has a white color or a red color. You are strict with the conditions. That is when we talk about the probability of A and the probability of B. That is what we mean about probability of A and B. That means your condition now is very strict. You want your car to be an Audi and you want it to be silver. So when we check that in a scenario of a Venn diagram, it has to be that intersection over there. That A and B over there. That I think that color is blue. So that is what we mean about probability of A and probability of B. There is something called in probability an additional rule or addition rule. I think we call it addition rule. Addition rule. That is when we now find the formula for that probability of A or B, which is probability of A or probability of A or B will be equal to the probability of A added to the probability of B, and then from there you subtract the probability of A and B. That is how we calculate the probability of A or B. We use the addition rule. That is what we call addition rule. You see, this addition rule can be, adapted for several scenarios. For example, when we talk about mutually exclusive events, when we talk about independent events, that addition rule looks different from one scenario to another. So that is what we are going to talk about now. the mutually exclusive events and what we call the independent event. So when we talk about what we call mutually exclusive events, that is two events that cannot happen at the same time. So what do we mean about that? Just an example, events that cannot happen at the same time. Just a quick example on top of my head. One, you cannot study in high school pure maths and at the same time study maths lit. So those two events are mutually exclusive because they cannot happen at the same time. If you are studying maths lit, then you are studying maths lit. If you are studying pure maths, then you are studying pure maths. These two events cannot happen at the same time. That is what we mean by mutually exclusive events. So let's say we have A is you studying pure maths. I will just say maths, which is pure maths. And then event B is you studying maths lit. So we say these two events are mutually exclusive because they cannot happen at the same time. So the scenario, this scenario in a Venn diagram is not similar to that Venn diagram that we see over there. Because what we mean by events that cannot happen at the same time, that means A and B do not exist. You can't start the maths lit at the same time and start the pure maths at the same time. So that is what we mean when we say A and B events do not exist. So something that cannot happen in probability, we say it has a probability of 0. So the probability of A and probability of B is equal to 0. When we say that the events are mutually exclusive. Mutually exclusive. That is what we mean when we say events are mutually exclusive. We say event A and event B cannot happen at the same time. In high school, you cannot register for pure maths and register for maths lit at the same time. That is what we mean. So that means the probability of you in your subjects having pure maths and having maths lit at the same time, that probability is 0. Hence, we see that probability of A and probability of B equal to 0 over there. This scenario is represented in a Venn diagram using a far different scenario from what you see on that Venn diagram. Because if you look at that blue color over there, which is the intersection, that intersection is a scenario whereby it's you that is studying pure maths and studying maths lit at the same time. And we say that intersection does not exist. It does not exist. It's impossible. You can't register for maths lit and pure maths at the same time, which means the cell of A has to be apart from the cell of B, which is the Venn diagram for mutually exclusive events. So these circles have to be apart, circle A and circle B. The reason why they are apart is because these two events are mutually exclusive. And then remember we said that the additional rule changes from one scenario to another. If you look at the additional rule at the bottom over there, the last term is about the probability of intersection. So when we have mutually exclusive events, that probability of intersection, probability of A and probability of B is 0. So in a scenario whereby they tell you that these two events are mutually exclusive, it's very important that in your addition rule, you remove that last term. because it is 0. That last term will be minus 0, which is basically nothing. Remember, these two events are mutually exclusive and their probability happening at the same time is 0. That's why when they tell you that these two events are mutually exclusive, you just have to remove that last term and be left with the probability of A is equal to probability of A or B is equal to probability of A plus the probability of B. Keep that in mind. That is mutually exclusive events. It will come up later on. And then another thing that you have to think of when it comes to events is the terminology or the concept of independent events. That as well has an effect when it comes to the additional rule. When we talk about independent events now, we talk about events that are not dependent to each other. For one event to happen, that event is not dependent on another. It is not being affected by the occurrence of another event. A quick example on top of my head is the probability that you pass mathematics and the probability that your friend passes mathematics as well. Those two events are actually independent. Well, I assume they are. So whether you pass maths or you do not, then that event is basically not independent. Is not dependent on the occurrence of whether your friend passes maths or he does not. You go and write the exams on your own, using your own intellectual capacity. So the event of you passing that maths test cannot really be dependent on whether your friend is going to pass that maths. So that is the example that I have on top of my head. Is there anyone that would like to give us an example of what we mean by independent events? Just one scenario. Anyone with a quick example? Okay, now let me proceed. Let's say we have event A and event B, and then how do we see that event A and event B are actually independent? We see this by that measure. The probability of A and B happening have to be equal to the probability of A multiplied by the probability of B. If you are given a scenario whereby you want to show that certain events are independent, you will have to calculate the expression that is on the left-hand side, put it aside, and then calculate the probability of A, calculate the probability of B, and multiply those two probabilities and put them aside. Check if those values that you get are equal or not. When they are equal, then these two scenarios are independent. It goes back to being independent. When these two values are not equal, then these two events are not independent. So that is how you check whether two events are dependent or not. You calculate the probability that A and B happen. You calculate that probability, you put it aside. You calculate the probability of A, you calculate the probability of B, and then you multiply the two probabilities to get that product. Once you get that product, you compare to the value that you have calculated earlier and check if they are equal. So if they are equal, then these two events are independent. If they are not equal, then these two events are not independent. So that is how you check the dependence of events.
Yeah.
Okay, I think there is a question. I like questions.
I have a question.
Sure.
Could you please repeat this independent events thing and like how do you calculate P, A, and B? Because I got lost somewhere.
Okay, no, that's good. I can. We are dealing with the concept of independent events. We say that the way we see whether two events are independent or not, we use that formula. Independent events can be a scenario whereby we talk about your gender and we talk about you passing a certain test. We want to see whether passing a certain test is dependent on your gender or not. So that is what we mean about dependence. Another thing we talk about is a scenario whereby we say, if you passed a certain test, does that mean, is you passing a certain test dependent to your friend passing a certain test as well? Are these two events dependent or not? So the way we check for that, we use this formula. We calculate the probability of A and B happening. We put that probability aside. I will show you how to calculate probability of A and B later on. So you calculate probability of A and B happening, you put it aside, that value. You also calculate the probability of A, and then you calculate the probability of B, and then you multiply those two probabilities to get that product, and then you put that product aside. You will see later on how to calculate the probability of A and B, and you will see later on how to calculate probability of A and probability of B. And then after you have calculated those two values, you check if they are equal or not. If they are, that means these two events are independent. If they are not, then these two events are not independent, which means they are dependent. Is that clear so far?
Yes, thank you, sir.
Okay. So this also affects the additional rule that we talked about earlier. I think you remember the rule that we discussed, the additional rule that we talked about earlier. So the additional rule was like probability of A or B is equal to probability of A plus probability of B minus probability of their intersection A and B. So when we are told that these two events are independent, there is something that we can change in this formula, which is the last term. We can change the last term because we are told that these two events are independent. And once we are told that they are independent, we know that the product of probability of A and the probability of B is equal to the probability of the intersection, or the probability of the intersection of A and B is equal to the product of those two probabilities, probability of A multiplied by the probability of B. So if we are told that these two events are independent, then we can replace the last term there with the probability of A multiplied by the probability of B. Because we know that these two events are independent, and the probability of A and the probability of A and B is equal to the probability of those two events. That's why we replace that last term. We know that these two events are independent. There are a lot of things that we can discuss as well, such as a tree diagram, such as a Venn diagram, such as a contingency table. So let me just briefly introduce you to what we mean by tree diagram. You remember the scenario that we had earlier, right? When we talked about a box full of balls. Remember the out of those 10 balls, 6 of them are black and 4 of them are white. So 6 is black balls and 4 is white balls. And then in total, these balls are 10. So we can represent that scenario in a Venn diagram. In a tree diagram. So what do I mean by that? So this is the discussion of a tree diagram. Now let's say you go and take one ball out of that bag. You have two options. You can take out a black ball, or you can take out a white ball. You have two options when you go and take out that ball. So what is the probability that the ball that you take from there is black? What do you think is the probability that you take a black ball? This is something that we covered earlier.
6/10.
That is 6/10. Just to mention a quick thing, it's important that you stop me in the middle of whatever that I'm saying if you have a question. That's very important. I don't want to leave any learner behind. Make sure that if there is something that you don't understand, make sure you stop me in the middle of whatever. I'm happy to explain again and again and again until you understand it. So the probability that you take a black ball is 6/10. The reason why we say 6, it's because out of that box, there are 6 black balls. The reason why we say divide by 10, it's because out of that box, or in that box, there are 10 balls. And then the probability that you take a white ball is 4/10. So now you take that ball and you keep it to yourself. After you keep that ball to yourself, how many balls are left in that box?
Nine.
Yeah, there are 9 balls that are left. So you go for the second time now. So let's assume now you took the black ball. The ball that you have kept to yourself is a black ball. So that means the ball that you kept to yourself is a black ball, okay? So you keep it to yourself. So if we assume that it is a black ball, that means we are going to take that branch, that upper branch, because that is the one that leads to a black ball. And then from there, we can say, okay, for the second time now, you still have 2 options. Your first option can be black. Your second option can be white. You are going to take the ball now for the second time. Remember, the ball that you have kept to yourself is a black ball. So that's why we use that branch of black. We are assuming that the ball that you are keeping to yourself is black. That means there are 9 balls left in that bag. But as much as there are 9 balls, how many black balls are still left there?
5.
5 of them. Remember, we are assuming that you took the 1 black ball. So that means out of 6, there are 5 black balls now. But how many white balls?
4.
4, because we are assuming that you did not take the white ball.
Yeah.
So
Yeah.
the total number of white balls remains the same. So the probability that for the second time you take the black ball is 5/9. The probability that you take out the white ball is 4/9. The reason why we have a 5 now, not a 6, is because we are assuming that the ball that you took at first is black, which means out of 6 balls, there are only 5 remaining. The reason we use 9 is because there were 10 balls at first, and then you took out that first ball, and then you are remaining with 9 balls, hence 5/9. I think that one is clear. So now we put the assumption of taking the black ball at first, put it aside now. We assume that the ball that you took is actually not black, it's white. Hence, we are going to use that branch now when we talk about the tree diagram. We are assuming that the ball that you took first is not black, it's actually white. So we're going to extend now from that branch at the bottom. Still, we have 2 options. We have the option of taking a black ball. We have an option of taking a white ball. So let us do the math. If we take the white ball, how many black balls are still there in the box?
6.
6. They are still white. There are still 6 black balls. If we took the white ball, how many white balls are remaining in the box?
3.
3. So this will be 3/9. That will be 6/9. So this is what we mean by a tree diagram, and that is how you construct the tree diagram. Are there any questions with regards to the process of constructing a tree diagram before I dive deep into the questions that might pop up when it comes to the tree diagram? Any questions? So far, so good, that's fine. So the question that might pop up is a question of what is the probability that at first you took a black ball and then the black ball was followed by a white ball? Remember, the order in this case is very important. The question said, at first you took out a black ball, and then that black ball was followed by a white ball. So it's black followed by white. So that is the probability of, let me write it where. Let me clean that. The question is, what is the probability that the first ball that you took is black and this black ball is followed by white?
Sorry, sir.
Okay.
There was a statement that you were saying, actually you're saying if you take out black ball, actually it was white. If you take white ball, the balls will remain white. Actually, they will remain. I don't get that statement. You were saying if you take out white ball, then the balls will remain black.
Or maybe I was saying, I'm not sure. Maybe I was saying, if you take out a white ball, the 6 black balls will remain as 6 because you did not take out a black ball. You took out a white ball. So if you take out a white ball, those 6 black balls will remain as 6. Maybe that is what I was saying.
Okay.
Do you understand it?
Yeah.
Okay, no, that's good. So in this scenario, they say the first ball that you took is black and then followed by a white ball. Be very careful in this question because they said the first ball is black, and then the second ball is white, meaning that the order is important. So what do you think will be the answer for that question? I think let me write it down for this one, and then you can answer the following one. So you see that the first letter is black. You go to the beginning of your branch. You follow the branch that will lead you to black. There is that branch. That branch has a probability of 6/10. And then you write that 6/10. You multiply. As you are there at B, which is black ball, that means you took out the black ball and the probability was 6/10. The question says the black ball must be followed by a white ball. So as you are taking a break there at black ball, you have a decision that you make now. Do I go for the black ball or do I go for the white ball? The question says the black ball must be followed by a white ball. So you follow that white branch, and it has a probability of 4/9. You multiply that 6/10 by 4/9. Then that is your probability. It's very important that you notice that when we move through a branch, we multiply. We will talk a different scenario later on when we add. I will also show you when do we add. So I want you to take note that when we move through a branch, we move with a multiplication. We moved through B, and then we moved through white. That is 6/10 multiplied by 4/9. And then that will give you 4/15, I think. Hopefully my calculator is right. So this is the question where they said the first ball, okay?
Sorry to interrupt you. So that comma there by B and W, is that and, or what is that? What does that comma mean?
Is black followed by white?
Oh, so it's not black and white.
No, it's black followed by white.
Okay, thanks.
Yeah, it is black followed by white. It's a different scenario when they say black and white, and we are going to get into that later on. They might say black and white, whereby the first ball is black, then they mean the same thing. When they say black and white, whereby the first ball was black. Because the order in this case is very important. You will see that later on. That is where I'm going to basically. Another question might be a question whereby they ask you, what is the probability that the first ball that you took was white and then followed by a black ball? White followed by a black ball. White followed by a black ball. So that would mean probability the first is white followed by a black ball. So what do you think will be the answer in this case?
Over 15.
I wanted the thinking process behind, not the answer. How did you get there?
I think it's 4/10 multiplied by 6/9.
It is 4/10 multiplied by 6/9. Yep, that is correct. You check your order. The first ball has to be white, so you go at the beginning of the branch. The first ball is white, which is 4/9, multiplied by another ball. The second ball has to be black, so you take that upper branch, which is 6/9. And then that should give you a 4/15 as well. A 4/15. If you remember, when I was asking those two questions, I was emphasizing the thing of the first ball is this, the second ball is that, the first ball is this, the second ball is that. So expect that kind of a question, but there's another question that might come up, the one that does not necessarily obey the order of whether the first ball was black or white. It will ask you, what is the probability that the two balls that you took were black? The balls that you took were black or white? What is the probability that the ball that you took was what is the probability that the two balls that you took were black? Okay, what is this question? Okay, there's end. It's end, it's not or. What is the probability that you took out a black ball and a white ball? Probability that you took out a black ball and a white ball. It does not matter now whether the first ball that you took was black or the first ball that you took was white. It has to be a combination of black and white. Strictly the combination of black and white. Black and white. You will go to your Venn diagram, to your tree diagram, and observe the branches that give you black and white. If you observe that that upper branch, there is B, there is W, there is black, there is white. So if you take the first ball as a black, and then you take the second ball as a white, that means you got that combination. Your two balls are black and white. One of those balls has to be black and one of those balls has to be white. So it's a combination of black and white. But that is not the only combination of black and white that is on that tree diagram. There is another combination. It has to be the white ball at first, followed by the black ball. So when you answer this question, you have to consider both branches. You have to consider both combinations. You have to consider both branches. You have to consider both combinations, because it's a question of what is the probability that the balls that you took are a combination of black and white, regardless of whether white you took it at first or black you took it at first. Regardless of that pattern, I just want a combination of black and white. This is now whereby you say the probability how can I write this one? I want a mathematical notation. A probability that it's a combination of black and white. Probability that it's a combination of black and white. It's a combination of black and white, regardless of the order. This is whereby now you will have to accommodate both branches. You will talk about the upper branch, signaling whereby the first ball was black, followed by the white ball. Remember the probability of that, we said the probability of black followed by white. Remember now we move from the upper branch to the lower branch. That means we jump now from one branch to another. At the beginning, we moved through a branch from black to white, and then we multiplied. We moved through a branch from black to white, we multiplied. From white to black, we multiplied. But now when we move from the upper branch to the lower branch, we have to add now. When you jump from one branch to another, you have to add. When you move through a branch, you have to multiply. So keep this in mind. When you move through a branch, you multiply. When you move from one branch to another, you add. So the first combination of black and white is black at first, followed by white. Another combination is white at first, followed by black, which means we jump from the upper branch to the lower branch. That means we add over there. The reason why we add, it's because we moved from one branch to another. And then these probabilities, we have calculated them before. They are actually up over there. That is 4/15 plus 4/15. And then I think when you press that on your calculator, it has to be 8/15. No, 8/15. 8/15. Are there any questions? Before we move to what we call a Venn diagram. 8/15. So this is a question of a combination of black and white, regardless of whether the first ball was black or the second ball was black. This is the question of a combination, regardless of the order. But the upper questions that we answered were questions that were very strict when it came to the order. So the first question had to be about a black ball that comes out first, followed by a white ball. The second question was about a white ball that came out first, followed by a black ball. So that is the difference between those two questions. And then this one, it's a combination now. It's an order of black or white. Those two balls that you have to be black or white, black and white. One of them has to be black and one of them has to be white, regardless of which one came out first. Are there any questions with regards to what we have done? Before we move to, I think we will just move into contingency table, because we have done a Venn diagram before. Any questions? Everything clear so far?
Everything clear, sir. Thanks.
I like questions. Please don't hunger me. The more we engage, the more we learn, I believe. So now we will talk about contingency table. Contingency table is whereby you can expect the question of independence. Contingency table. When we talk about contingency table, it can be a representation of a scenario. Let's say in your school, I don't know how many learners are there in your class that are taking maths, but let us just assume that there is 30 of them. Let's say there are 30 learners in your class that are taking maths. So we can represent that in a contingency table. And that is what I'm sketching over there, which is a contingency table. Out of those learners that are in your class, some of them are boys and some of them are girls. So the first column there will be about boys that are in your class. The second column will be about girls that are in your class. And then when we talk about the rows, let's say you wrote a mathematics test and now the results are out. So those two rows are about the number of learners that passed that maths test. And then another row is about the number of learners that failed that test. So the first row is about boys that are in your class. The second row is the second column. The first column is about boys that are in your class. The second column is about girls that are in your class. The first row is about learners that passed the test. The second row is about learners that failed the test. So let's say in your class there were there were 16 learners. In fact, there are 16 learners, and we say 6 of them are boys, and we say 10 of them are girls. And out of that 6 boys, we say 5 of them passed the test. So that 5 over there means 5 boys passed the mathematics test. And then what do you think will be the number of boys that failed the test?
1.
Yep, 1. That will be 1. And then let's say we are told that out of the 10 girls that are in your class, 3 of them failed the test. How many number of girls passed the test?
7.
Yep,
7.
7. So how did you get to 7? I like the thinking process, not the answer.
10 minus 3.
Yep, we said 10 minus 3. The total number of girls that are there is 10, and the total number of girls that failed is 3. So if we want the total number of girls that passed, it has to be 10 minus 3, which is 7. So now, if we look at that contingency table, it is not complete. We need to find the number of learners that passed and the number of learners that failed. What do you think we should place in this cell as the number of learners that passed?
You must say 5 plus 7. Which
5
is
plus
12.
7, which is equal to 12. 5 plus 7, which is equal to 12. Thank you very much. You gave me your thinking process before the final answer. What do you think we should write here as the total number of learners that failed the test?
1 plus 3.
1 plus 3, which is equal to 4.
Yeah.
So if you look at 12 and 4, those numbers are not about the gender. 12 is just about learners that failed, that passed. 4 is about learners that failed, not about the gender. 6 is about boys, and 10 is about girls, regardless of they passed or not. Then the conditions become in that 2 by 2 cell, which is 5, 7, 3, and 1. The conditions whereby we talk about a boy that passed, we talk about those 5 learners. If we talk about girls that failed, we talk about those three learners. So now in this question, you can expect in this contingency table, this is total, that is total. So how many learners were there? 16 of them. That cell over there at the corner is the total number of learners that were there, which is 16. So the question that you might expect, what is the probability that a boy passed that test?
5/16.
A probability that it's a boy and the boy passed. So what is the probability? 5/16. You will check that combination. There is a boy, so there is a boy. There is passed, there is passed. So it's boy, passed, boy, passed, boy, passed. Their point of intersection is that 5. Then you will take that 5 as a numerator, because that 5 is the number of boys that passed. And then you divide by the total number of learners that were there. When we talk about the probability that it's just a boy, regardless of whether he passed or not, it's just a boy, what do you think will be the probability?
6/16.
That will be 6/16. what is the probability that the learner passed, regardless of the gender?
12/16.
The probability that the learner passed, that will be 12/16. You will move from passed and check the total number of learners that passed, which is 12, and then the total number of learners that wrote, which is 16. Now you will encounter a question here whereby they ask you to check the independence between the gender and whether you pass the test. Is the event that you are a boy contributing to whether you are going to pass the test or not? Is the event that you are a girl contributing to an outcome whether you are going to pass a test or not? So that is where we check the dependency now. Well, this is a scenario whereby statistics proves the people that okay, let me stick to maths. This is whereby we check whether your gender contributes to the outcome of you failing mathematics or not. These two events, are they dependent or independent? If they are independent, that means regardless of whether you are a boy or you are a girl, the outcome of passing a certain test is not affected. That means they are independent. They do not affect each other. So how can we check that these two events are independent or not? How can we check the dependency between the gender and passing? You will have to check the probability of A and B equal to probability of A times the probability of B. That is what we want to check. Is this the case or not? A can be anything from the columns. You will take A as anything from the columns. Let's say A is the event of being a boy. You can take girl as well. It's up to you. And then B will be any event from the rows. So you take A from the columns, you take B from the rows. B can be anything. Let's just say B is passed. So you can take fail as well. You can take failed, it's up to you. So we want to check now if the probability that, hello? We want to check if the probability of a boy and passed is equal to the probability of boy multiplied by probability of passed. We want to check if those two things are equal. Remember, we do not know whether this is correct or not. We just want to check that. I think we have calculated the probability of A and the probability of boy and passed. The probability that it's a boy and he passed, I think we have calculated that to be 5/16. Also, we have calculated the probability of a boy. Also, we have calculated the probability of passed. So I think what we need now is the product of probability of boy with the probability of pass. So let us calculate that. Probability of boy multiplied by probability of pass. What that will become, what was the probability of boy? I can't remember.
It was 6/16. It was part of probability.
It was 6/16. What was the probability of pass?
12/16.
12/16.
12 over 16. What do you get when you press that on your calculator?
9 over 36.
9 over
32.
32. So what can you conclude about these two events? Are they dependent or independent? Remember, the probability of boy and pass is equal to 5 over 16. So what can you conclude about the dependency between the gender and passing a test?
They are not dependent.
They are not dependent, which means they are independent, because these two values are not equal, which means this requirement is not valid, the one that we wrote upwards. So whether you pass a mathematics test or you fail it, that does not depend on whether you are a boy or you are a girl.
Sir,
Hello?
so didn't you say that for events to be independent, the P probability of A and B has to equal to probability of A times probability of B?
Okay.
Do you not say that?
Oh yeah, I did. Oh, okay.
So these are
Comes
not
back
equal.
and bite me now. Yeah, it comes back and bite me. It does not allow me to make the conclusion that I wanted to make. Well, we said that if the probability of A and B is equal to the probability of A multiplied by the probability of B are equal, if those two things are equal, then we can say that the two events are independent, which means they do not depend on each other. So if they are not equal, then that means they depend on each other. Ish. No, it was just a random example that I took out of my head. So in this scenario, we see that they are actually not equal. So we can conclude that these two events are not independent, which means they are dependent. They are not independent, which means they are dependent. Yeah. So that means an outcome of you passing a mathematics test depends on your gender. Nah, that can't be correct. This is an example that I just took out of my head. It can't be true. You can pass maths even if you are a male or a female. So yeah, that is what I wanted to discuss with regards to the introduction of the concepts and everything. Let us dive deep into an example now. Are there any questions so far before we get into an example? Any questions? Okay, no, sounds good. There we have event A and event B. Suppose that probability of A, we are given that the probability of A is equal to 0.4. Also, we are given that the probability of A or B is equal to 0.7. So the questions that we are going to do are sort of exam type questions. So I took the screenshots of the previous question papers. The ones that we did were just introduction. They were coming straight from my head. Then the probability of B is equal to K. Yep. So we are given in question A that event A and event B are mutually exclusive. So let us calculate the value of K if these two events are mutually exclusive. What do we mean by event A and event B being mutually exclusive. What do we mean by that? Any guess?
They can't happen at the same time.
Yeah, they can't happen at the same time.
So it's 0.
The probability of A and B has to be equal to what?
0.
Yeah, it has to be equal to 0. So that is what we mean by mutually exclusive. So let us move forward then and answer the question. Do you still remember the addition rule that we talked about? Probability of A
Yes.
or B is equal to probability of A plus probability of B minus probability of A and B. So we are going to use that addition rule. What are we going to substitute for the first term?
Um, 0.7.
Yep, we are going to substitute 0.7. What are we going to substitute for probability of A?
0.4.
0.4. What are we going to substitute for probability of B?
Okay.
What are we going to substitute for Jehovah? What are we going to substitute for probability of A and B?
0.
0.
Yep, excellent. The reason why, it's because these events are mutually exclusive. So let us solve then for K. I think I get 0.3. What do you get?
0.3.
Yep. So you see now the concepts and everything that we discussed have become valuable because you know the concept of mutually exclusive. You know the addition rule. So let us move to independent events. Now we are told that A and B are independent events. Remember the probability of A is 0.4, just in case you can't see those small numbers. Probability of A or B is 0.7. Probability of B is K. So I just wanted to think about number B. We are given that event A and event B are independent events. So how do we use that given information to calculate the value of K? First of all, what do we mean by independent events?
They do influence. They don't. Yeah. They don't influence each other. I think.
They equal each other.
Okay, yeah. If the events are independent, that means they do not depend on each other. But the expression that makes us, the mathematical definition of independent events revolves around the probability of A and B. What is that expression? What should I write on the right hand side?
Probability of A times probability of B.
Yep, probability of A times probability of B. So let us go further and substitute. What is the probability of A?
0.4.
0.4. What is the probability of B?
It's K, which is 0.3.
Okay. So the probability of A and B is equal to 0.4 times K. That is the information that we get from the independent, the independency given information.
Can you not say 0.3?
Hello?
Can you not say 0.3 instead of K?
No, it's a different question.
Okay.
Yeah, it's a different question. Remember, we were told at A that these events are mutually exclusive. Now they change the condition and say these events are independent. So it's two different questions. We are still calculating for K.
Tango.
Okay. So the addition rule is probability. We use the addition rule again. Probability of A or B is equal to probability of A plus probability of B minus probability of A and B. As we have seen before, we substitute over there by 0.7. We substitute probability of A by 0.4. We substitute probability of B by K minus. What do you think what are we going to substitute that last term with?
I think 0.4 times K.
Yep. It has to be 0.4 times K. And then we collect like terms. We take that 0.4 to the left, and then it subtracts from 0.7 to get a 0.3. And then we will be left with K minus 0.4. That is like saying X minus 2X. So how do you solve that? How do you add those two things? What do you get?
Sure.
Sure. I don't know about you, but I'm getting 0.6 times K. Are we still together?
Yeah.
Okay. I'm getting 0.6 times K. When I add those two things, K and 0.4 times
Yeah,
K.
it is 0.6K.
Yep. And then what do you think we should do?
I mean, I'm lost.
Oh, okay. Very good.
How
Very
did-
good. I want the
how
lost
did you-
one. Come.
Yeah, I'm also confused.
Yeah, I want the lost one. I want the confused one. Come.
How did you get 0.6K?
Oh, very good. So you are lost on that part as well, which is
Yes.
0.6. Oh,
Yes.
very good. I want the lost ones. So let me take you back to grade, what was it? Grade 5, grade 9. What is 2x minus x?
X.
It's going to be x, right? Because you took the x and then you said 2 minus 1, because there's a minus 1 there. So what is k minus 0.4 k? You will take a k, and then there is a 1 there. There is a 0.5, there's a 0.4, negative 0.4 there. So it will be your 1 minus 0.4, which will give you a 0.6. Hence, you will place a 0.6 there. Should I explain it further?
I'm still lost.
Oh, that's good. I will try another method.
Because when I put 1 minus 0.4 on my calculator, I get 3/5.
Press that SD on top of DEL.
That is 0.6.
3/5 is 0.6.
Yeah.
Oh, okay. Now I get it. Thank you.
So are we together now?
Yeah, we are together.
Very well. Very well.
Sure.
Sure.
What I don't understand is like Yabona there by that P of A and B. How did we get from that to P of A or B?
You are referring to this part, right?
Yeah, how did we move from that to the next one?
How did we move from probability of A and B to
To
probability of A times probability of
No,
B?
No, how did we move from probability of A and B to probability of A or B?
Yeah.
Okay, your question is confusing me. Which part?
Sir, yabona apa
Sure.
P of A and B.
Hmm.
How
Yeah.
did we move from up to upper Zans, like the next one, the very next
Too
one?
late.
Yeah.
Yeah.
Oh no, these are two different things. The one that I will write with a red what? That is an addition rule. So this is something that you copy directly from your formula. Something that we talked about earlier. Do you still remember the addition rule?
I remember you teaching that.
Yeah, that is the addition rule. So it
So-
is sure.
So is you introducing this formula just trying to get that P of A and B?
Yeah, I'm trying to calculate K.
Okay. Now,
We dealt with the first part, the one that I will highlight with the color that I don't know. I think it's blue. You see the one that I'm highlighting with blue over there. There we were working with the given information, which is these two events are independent. We were trying to understand what it means for these two events to be independent. We said that the probability of A and B has to be equal to the probability of A multiplied by the probability of B. And then we said that is equal to 0.4, which is the probability of A, multiplied by K, which is the probability of B. And then we were done with that part.
okay.
Because that was about independent events. And then we moved to the lower part, which is about the addition rule. Hmm? Sorry? I was just writing the addition rule over there, which is the probability of A or B is equal to probability of A plus probability of B minus the probability of intersection. I was just writing down a formula there. And then we said this is given, which is 0.7, probability of A or B, it's given. The probability of A is given as well, it's 4. The probability of B is given to be K, which is K, the one that we want to calculate. And then the probability of A and B, that is the one that we expressed using the given information of independence. We expressed this one to be 0.4 times K. Hence, we substitute with 0.4 times K over there. And then we move down, we take the 0.4 from the right to the left, it becomes a negative, which is 0.7 minus 0.3. And then we add that K minus 0.4 times K. We use what we learned from grade 7, standard 5. Sure.
Why are you minusing 0.3, not 0.4?
Oh,
Isn't
no,
0.3 the answer?
I was just checking if you are awake. That's all.
Oh,
I was just checking if I'm still with awake learners here. It turns out that, yeah, you are. And then what we add from there, K minus 0.4 times K, we get 0.6 K. So on the left, we'll get 0.3 there. 0.3, and then we divide by 0.6. We divide by 0.6. What do you get for K?
a half.
0.5.
Is that so?
Yes.
Yes, 0.5.
Yeah, it has to be a half, which is 0.5. So that is how we deal with with mutual exclusive events, independent events, and stuff like that. Are there any questions?
And I'm good, sir.
Okay. Are you good with how we added K with the negative 0.4K? Okay. Before we go to the permutation factorial, which is counting principles, before we go to that, let us do this exam type question, which is on Venn diagram. We have dealt with the tree diagram. We have dealt with mutual exclusive. We have dealt with independent. Now we are only left with, we have dealt with contingency as well. We have dealt with, we are only left with Venn diagram. Then we dive deep into what we call factorial and stuff like that, if there's still time. Can you see that diagram, that given information? Or is it too small?
You can perfectly see.
Oh, that's fine.
Yes,
That's fine.
yes.
So we are given here. Is there a learner that would like to read for us? Please.
Complaints about a restaurant fell into three main categories: the menu M, the food F, and the service S. In total, 173 complaints were received in a certain month. The complaints were as follows: 110 complained about the menu, 55 complained about the food, 67 complained about the service, 20 complained about the menu and the food, but not the service. 11 complained about the menu and the service, but not the food. 16 complained about the food and the service, but not the menu. The number who complained about all three is unknown.
Okay, very well. Thank you very much. Let me just go through it again with explanation at the moment. So this is about complaints that were made in a restaurant. And these complaints were in three categories. Some complained about the menu, some complained about the food, some complained about the service. And then in total, we are told that these complaints were 173 in that specific month. So the complaints were, well, before we move, that 173 is what we call the sample space. Do you still remember when we were discussing about sample spaces? That 173 is what we call a sample space. That 173 over there. Now, we are told that these complaints are listed in this way. 110 of them complained about the menu, 55 complained about food, 67 complained about service and stuff like that. So if you look at this, we have three things: the menu, the food, and the service. So how do we then draw the Venn diagram? Because if you look at the first question, it says, draw a Venn diagram to illustrate the above information. A Venn diagram is appears in a box like that, I think, as we have seen before. A Venn diagram appears in a box like that. Remember, the total space, which is NS, is equal to 173. We know that there are 173 complaints there. And we know that there are three cycles that we expect. Maybe they will intersect, maybe they will not, but there are three cycles. There is menu, there is food, and there is service. And looking at the three things, at the three details over there, those three details about 12, 11, and 16, it seems like there are some interactions between these three things: main, food, and service. Also, if you're looking at the last information, the number who complained about all three is unknown, which means there is a number of people that complained about all the three, which is the intersection now. There is that intersection, but that intersection at the moment is unknown. So we can expect an intersection between the three circles. So let us draw the first intersection, which is the first circle, which is for menu. Another circle, which is for, let's say, food. Hopefully, we are not getting hungry on that side once we talk about food and menu. Another third circle, it has to be about service. So there is an intersection over there of which we do not know what it is at the moment. We do not know the number of complaints that fall into that circle, into that intersection. So when you sketch a Venn diagram, it's very important that you start in the middle. When you fill the details, it's very important that you start in the middle. That is what I would suggest. You start in the middle. It might be a different story for another example, but in a scenario like this, it's very important that you start in the middle. So the middle over there is about the number of complaints that were about the menu, and the number of complaints that were about food, and the number of complaints that were about service. And remember, we were told that the number of those complaints are unknown at the moment. So that will be X. That will be X. So we are done with the last instruction. Remember, we start with the center, which means we start at the bottom. So we are done with the number of complaints that were about all the three things: menu, food, and service. So then we are going to deal now with the three other details. Remember, we start at the bottom. So now we're going to deal with 20, 11, and 16. So that is, we deal now with those intersections over there, those bigger intersections. That is what we are going to talk about at the moment. Those bigger intersections over there. We want to fill those spaces. So let us discuss it. Is there someone with an idea? What can we write between M and F? What can we write there? What is the information about menu and food? How many complaints about menu and food?
20.
20 minus X.
Do we write 20 minus X or do we write 20?
20 minus X. 20 minus X.
20.
20.
20.
Oh, 20. Yeah, 20.
I knew that there's going to be a debate here. Is it 20 minus X or 20?
20.
Very good. It is 20. Why do you say 20? I wanted the reasoning process, not the answer.
Yeah. Because it says, they are complaining about menu and food, not service.
Yeah.
So it's 20
So
minus.
it's about menu
Not all
and food.
Food only, yeah.
Only
Yeah,
menu.
it's about menu and food,
Food.
not service.
Yes.
Which
Yes.
means in that 20, the X has been excluded already. So do we understand each other?
Yeah.
So if that part was not given, if this thing, but not the service, if that part was not given, then we would say 20 minus X. x.
Yeah.
So analyze the given details. When they say but not the service, that means that has been excluded already. But when they say the complaints about menu and food, that means the bigger intersection, which includes that X. But when they say about menu and food, but not the service, that means that X has been excluded. So it is 20 over there. So what do we write between menu and service?
11.
11. Between menu and service, we write 11. What do we write between food and service?
16.
We write 16 over there.
Yeah.
It is the same story because there is that part. Hence, we do not subtract that X. So if there was no but, we would subtract that X from 20, from 11, and from 16 if there was no but. But if there is a but, therefore we do not have to subtract it. So let us now move now to the bigger circles. We are done with the smaller nyana things. Remember, we were told that the complaints about menu are 110. Are we going to place in that space 110 or what?
No.
No. Why?
Because we have the 11, the 12, and the X.
Yep. There is already something in that box of M. There is already something. So we must accommodate those things that are already there. So how do we accommodate them? We subtract them.
We subtract them.
Yep, from that 108. But be very mindful of this. This statement, it says 110 complained about the menu. They complained about the menu, which means the bigger box about the menu. Hence, we are not going to put that. Hence, we are not going to put that 120 in that remaining part of M. We were going to put that 120 in that remaining part if they said 110 complained about the menu only. So do you get my point now? If there was only in that question, in that statement, if there was only, they said 110 complained about the menu only, then we would put here 110 if there was only. If they said 55 complained about food only, we would put 55 over there if there was only. If they said 65 complained about service, we would put, if 67, we would put 67 there because there was only, if there was only, So now there is no only, that means we cannot put those values there. We have to accommodate what is already there. Did you get that, what I've just said, or do you want me to go through it again?
No, good.
Okay,
Go through it again, sir, because some of us, our network is lagging. So,
okay. I will say it again. The reason why we do not put that 110 over there, it's because they said 110 complained about the menu. That means the bigger circle of the menu, all of that big circle. So that means we have to accommodate for the 20 that is already there in that circle. We have to accommodate for X that is already there in that circle. We have to accommodate for 11 that is already there in that circle. We have to accommodate those things in that 110 by subtracting them. So we will say 110 minus 20 minus x minus 11 to get what we are going to write there. That is what we are going to do. We were going to put 110 there if that statement had an only. If they said 110 complained about the menu only. If there was only, then we were going to write 110 with no doubt. But there is no only at the moment. So let us accommodate for the things that are already there in that cycle. That is 110 minus 20 minus 11 minus x. So did you get what I just explained?
Yes.
Okay. I think this pen, this ink that I'm using is not so clear. Let me use a strong one. So we say 110 minus 20 minus x, no, minus 11 minus x is equal to, what do you get?
79 minus x.
79 minus x. So we place the 79 minus x q. 79 minus x. And then we move along. We go for food. At food, we will say 55 minus what?
Minus 16.
Minus in minus
Minus
x
16 minus
Minus
20
Minus 20, yeah.
minus x, right?
Yeah.
Then 55 minus 16 minus 20, that will be 19 minus x, right?
Yes.
19 minus x. And then let us move to s. Can you direct me? How do we calculate?
67 minus 16 minus 11 minus x.
67 minus 16 minus 11 minus x. What do you get?
40 minus x.
minus x.
40 minus x. And there is a hand that is being raised.
Good evening.
Eh?
I'm a bit lost.
Okay.
Molero, the menu
Okay.
said 110 complained about the menu.
Yes.
Now, why did you write 79 minus x?
Why did
Why?
I write 79 minus x?
Yes.
Okay. You see that information, they say the 110 complained about menu, right? Which means they include everything in that bigger cycle of M. So it would be wrong for us to come and write 110 here, because this small space here is for complaints that are about M only, not necessarily just menu. They're about menu only, those ones that are in that small space. But the 100 represent the complaints about menu, the total complaints about menu. So in that bigger circle of M, there are complaints that are already there, which is 20 complaints, X complaints, and 11 complaints. So we have to accommodate those complaints from that 110. Hence we say 110 minus those 20 complaints, minus those 11 complaints, minus those X complaints here at the bottom. 110 minus 20 minus 11 minus X. We are trying to remove the ones that are already there in that bigger circle. And then we get that, okay, that sums to 79 minus X. And then 79 minus X is that region whereby we talk about the complaints that are about the menu only. Is that clear so far?
Yes, it is. Thank you.
Okay. So that is the same reason why we wrote 19 minus X for F only. And then we're trying to find the one, oh, we have found the one for S only, which is 40 minus X. So let us analyze what is happening here. There are X complaints about menu, food, and service. There are X complaints about menu, food, and service. And then there are 20 complaints about menu and food, but not service. That 20 does not include service. That 11 does not include food. That 16 does not include menu. And then there are 19 minus X complaints about food only. There are 79 minus X complaints about menu only. There are 40 minus X complaints about the service. So that is what we mean about what is in that Venn diagram. So that means we are done with those three given information. Is everything clear so far? Because if you can't draw the Venn diagram, then you can't answer the following questions. So it's of no use for me to rush to answering the upcoming questions if you did not understand how to draw a Venn diagram. Sorted.
Yeah, I'm good, sir.
Sorted.
Yeah, thank you.
Yeah, I'm sorted.
Danko. So let us move to answering the first, or well, the second question, not the first. The second question is about, it's about what? Determine the number of people who complained about all three categories. What do you think they want?
They want X.
Yep, they want X. The number of people that complained about all three categories. So how do we think we should calculate X here? It's a very interesting scenario.
Don't you? Sir?
Sure.
I think because the sample space is 173, correct?
Yep.
So how about we equate everything that's in the Venn diagram to 173?
173, yeah.
Danko. That's how we do it.
Oh, stop off.
Remember, in some scenarios, you might have something that is outside of these three circles. You might have something that is written there.
Yeah, I see.
Oh, yeah, so that is something that is outside. Maybe let's say that will be 4, right? So that 4 will represent the complaints that were not about menu, were not about food, and were not about service.
Sir,
Sure.
So then if we had like 4 people that didn't complain about these 3 things, would that be written with the bullet points, or would we first have to calculate and then we realize that we have a number left?
No, we will have to write it before we calculate.
So it would be part of the bullet points.
Yes, it will be part of the bullet points.
Okay.
And it will be part of the bullet points, yeah. It will be part of that Venn diagram, and it will be part of the calculations that we are going to do from now onwards.
Okay, thanks, sir.
Yeah. But now we are confident that there is nothing there. There's no 4, there's no 6, there's no something like that. Why we are confident? The first statement said that complaints about a restaurant fell into 3 main categories. If you read that first statement, the complaints fell into those three categories. So that means whatever complaint is there, it has to be inside of those 3 categories. So we do not have a 4 that is lying around. That is the reason why we are confident that there's no 4 lying around. So if there was something that says there, let's say 4 customers did not complain, then we would put 4 aside. And then that 4 would be part of what we are going to add here. Is that clear?
Yes, sir.
Yes, sir.
Let's
Can we
move.
remove
So
the 4 first?
Sorry?
Before we start calculating, can we please remove the 4?
Yeah, okay, that's fine.
Thank you.
So we are going to say 173, let us start in the middle, is equal to x plus 11 plus 20 plus 16. So we are done with the middle part, which is x, and then we are done with 11, 20, and 16. So we are left with the 3 remaining parts: 19 minus x, 40 minus x, 79 minus x. 19 minus x, 40 minus x, 79 minus x. So if there was a 4 over there, we were going to add that 4 as well. Are we still together? But there is no 4, so we're not going to add it. 173 is equal to, let us deal with the constants first. So the first constant is 11. We add it to a 20. We add it to a 16. We add it to a 19. We add it to a 40. And then we add it to a 79. And that gives us 185, if my calculator is correct. We are done with the constants. Let us now go to the variables, which is x. We have x, 1x, a second x, a third x, a fourth x. If you observe that the first x is going to cancel with the second x because they have different signs. So out of 4 x's, we have 2, which means that will be negative x minus negative x, negative x minus negative x, negative x minus negative x. That gives us a negative 2x. Is there any confusion so far?
No, sir.
No learner behind. And then we take that 185, we take it to the left, it becomes a negative.
Yeah.
So it will be 173 minus 185, which becomes a negative 12. What do you think we should do?
Divide by
Divide by
negative 2.
-2.
What do we get as x?
6.
6. Are we happy with everything so far?
Yes, sir.
Yes, sir.
This 6 is the number of people who complained about all 3 categories. This 6. So this 6 is there at the center. This 6 is there at the center. So just a quick question. It's not part of it is not part of the equation of the questions. But how do you think we will calculate the number of people that complained about the menu only?
79 minus 6.
The people that complained about menu only, that will be 79 minus 6.
Yeah.
So what is that?
73.
73. What do you think will be the number of complaints about food only?
13.
I want your thinking process.
19 minus 6.
19 minus 6.
19 minus 13.
Huh?
Minus
-6, sir.
Oh no, I was checking if you are still awake. 13. What will be the complaints about
40.
services only?
40 minus 6.
40 minus 6. What will be that?
34.
34.
Mhm.
So if you are looking at this carefully, we are dealing with quantities, we're dealing with number of certain things. So in your calculations, in this example, I mean, it's number of complaints. So we wouldn't expect to find any negative number there. We wouldn't expect to have a -6, for example, because complaints can never be negative. It has to be, complaints can be negative in a sort of, yeah, you can give a negative complaint,
Like
but
these people.
complaints cannot have a negative quantity. It can't be negative 6 complaints, -4 complaints, you see.
Yeah.
Another thing, you cannot expect a fraction over there. You cannot expect, let's say, 0.5 complaints. You cannot expect 1.5 complaints. There's no such a thing. So your calculations have to make sense. Once you get a negative number, or once you get a fraction, surely you have to doubt yourself and go back and check your calculations. And what I'm saying applies only in this scenario. Maybe
Okay.
another scenario will be a case whereby a negative is expected, or a fraction is expected. So don't think you are wrong if you get a negative in a certain scenario. Maybe in that scenario, a negative is an acceptable number. A fraction is an acceptable number. But I'm just speaking with reference to this scenario. Okay, let us move forward. I think we have said enough. Let us move to the third question. Is there any brave learner that wants to read the third question for us slowly, preferable? Who hasn't read? Okay.
Determine the probability that a complaint selected at random from those received complained about at least 2 of the categories. That is menu, food, and service.
Okay. That is determine the probability that, oh, thank you very much. Thank you very much. Determine the probability that a complaint selected at random from these or those received complained about at least 2 of the categories. It's very important to take note of that at least. So at least means it can be 2 categories or it can be 3. 2 or more. 2 or more categories. So we want the probability that the complaint that is selected at random complained about at least 2 of the categories. How do we go about that? Any ideas?
Can't we just take the blue stuff? Because blue
Can't
is
we
just
take the blue stuff?
the blue numbers, because they are just 2, right?
Or the blue stuff? Oh, okay. So if you focus at the blue stuff, right?
Yeah.
That 20, oh, I can't take that one at the moment. Sorry about that. That blue stuff over there, which is 20, 11, and 16, that is about 2 categories. That 20 is about M and F, which is 2 categories. That 11 is about M and S, which is 2 categories. That 16 is about F and S, which is 2 categories. So, sorry about that, guys. The question says at least 2. So if you take only 20, 11, and 16, then your answer will be about exactly 2 categories, not at least. So it can be 2 categories or 3. That is what we mean about at least. It can be 2 or 3. 2 or 3. So when you take 20, sorry?
Can you explain what they want from, like, what is the question asking us? Because I think I don't understand the question itself.
Okay, that's a very good question. They say determine the probability that a complaint selected at random from those selected complained about at least 2 of the categories. So they're asking if we select, let's say, a complaint from that box of complaints, what is the probability that complaint will be about or will belong under the 2 categories or more? That is what we mean by at least. So the complaint can be about menu and food, or the complaint can be about service and food, or the complaint can be about menu or service. And then the complaint can be about all of these 3 categories. But the complaint in this case is not allowed to fall only under 1 category. So it can be 2 or more, 2 or 3, 2 or 3. Do you get the question now?
Yes, sir.
Okay. So let us think the question, the answer. The regions whereby 2 or more categories are intersecting. 2 and more. It can be 2 intersections or 3.
So how about we add all those, like the 26, 11, and 16, and then let that be the numerator, and then the 173 becomes the denominator.
Yes, 73 will be a denominator.
And can you just add the intersections, the 26, the 20, the 6, the 11, and the 16?
Yep.
That,
Yep,
Okay.
that is what we are going to do.
So it's
That's
53
so
over
smart.
173.
We are going to take 20. How many categories are there at 20?
2.
How many categories are there at 11?
2.
How many categories are there at 16?
2.
How many categories are there at 6?
3.
So all of these regions that we have talked about fall under what we say at least 2. So it can be 2 or it can be 3. It can be 3. How many categories is 13?
1.
So we are not going to bother about that one. How many categories is 73?
1.
So we are not going to bother about that as well. How many categories is 34?
1.
So we are not going to bother about that one as well. So we are going to say the probability that at least 2. That will be 20, 11, 16, 6 divided by 173. What do you get?
53 over 173.
Yeah.
53 over 173. Is that clear?
Yes, sir.
Yeah. Is there any other question that you would like to ask about what we have discussed? What would be the probability that the complaint falls only under one category?
So wouldn't it be 73 plus 34 plus 13
over 175?
over 175?
Yes.
So you're saying it would be 13?
Aye.
13 plus 73.
13, 73, 34.
Oh, over 1.
Why do you pick those ones?
Because it's only
Because
it's
they're
only
the
one.
only category. Yeah.
Yep. So it would be 73 plus 13 plus 34 divided by 173. Probability that the complaint that you get falls under one category, only one. So that is 73 plus 13 plus 34. What do you get on your side?
120 over
120 over
173.
120, yeah, over 170.
Okay. So what do you think would be another question that would come up here?
probability of menu and food.
Yep, probability of menu and food. Let me clean. Probability of, in fact, we can go to the next slide. We don't have to clean anything. Probability of
menu and food.
So what do you think would be the answer?
20 over
Menu and food.
Menu and food.
20 over 1 thing.
So that is probability of M and F. So what do you think is the answer?
20 over 175.
Is that so?
Let me check. I mean, it's 173.
What is the probability?
I have 20 over 173.
Me too.
Yo, are you guys sure?
So why are you making us start ourselves?
No, I'm
Is it
going
not
to give
70?
you.
Is it not 73 times 13?
No, don't worry. We'll get there.
Oh, now I'm confused. No, it is 20.
Oh,
No,
okay.
now I'm confused. Now I'm confused.
So there are those two questions there. that you
Yes,
must.
it is. It is 20 over 173. And then the second one, we're gonna say the numbers individually because you said only.
Oh, Michelle.
Very interesting. Very interesting. You see, when we talk about probability of M and F, we will go to an intersection where M and F intersect. And that intersection is 20 and 6. That is where M and F intersect. But when they start to say only M and F, that means that they want a region whereby it is the intersection of F and M only. Because you see that 6 includes the services. And that 20 is only for M and F. There is that important word there, only. So if they say the probability of M and F, you go to the intersection of M and F, to the intersection of M and the intersection of F. And that intersection includes 20 and 6. Hence, the answer will be 20 plus 6 divided by 173. Once now the question starts to have only M and F, you will have to focus only in a region for M and F and only M and F. What would be that region?
$20.
Yeah, 20. Is it clear or?
It's clear.
Yeah, it's getting clearer.
It's clear.
Oh, okay. I thought I lost you.
You found us.
You're doing a good job. You're doing a good job.
You found.
So let us move to another question that is very similar to what we have just done. Now I want the probability of F and S, just to test if you understood what we have discussed. Probability of only F and S. How do we go about those ones?
So they're asking for the whole region of F and S. So it's 16 and 6.
Okay. Next one.
And that would be F and S is just 16, correct?
Yes, because it has the only part. There's a lady that did not understand this part. Are you with us? You're quiet.
Yes, I am.
You understand everything.
Yes.
No, that yes comes with a doubt.
So I'm slightly confused, like, why are we including 6?
Why are we including 6? Okay.
Yes,
Here,
because I
right?
feel like the 6 has all of them. So why are we including it for both of them when the 6 isn't like for everything?
The question was not specific. It was not strict. It did not add the condition of only.
Okay.
The condition is M and F only. No, the
So-
condition is M and F, right?
Yes, sir.
So when we go to our whatever, when we go to our diagram there, we check for M and F where they intersect. Just M and F where they intersect. You will see that we're talking about that region.
Okay, I get it.
You see that region includes it includes 20 and 6.
Yes.
That region is for M and F. But we talk a completely different story when we talk about only M and F.
Yeah, I understand that one.
Yeah. Only M and F will have to be only that 20.
Yes.
Okay.
Okay.
So these questions are about the intersection. Let us now go to OR, because there are cases of OR. If maybe they said M or only M, what would be your answer if the question was probability of M or F? Probability of M or probability of F, I mean, of M or F. What would be your answer? No, I think we should close the class at 9. It's been too long.
Wouldn't it be P of M plus P of F?
P of M,
yeah,
plus P of F. Is that all?
Minus P of
M
and F.
Yep, that is 100% correct. So what would be your probability of M?
73. Yeah.
Are you guys sure?
I know.
This is not only M, it's M.
Oh, okay, then it's going to be 73 plus 20 plus 16 plus 11. Yeah.
Are you guys with us?
Yeah.
110. Is it 110?
Yes.
If it was probability of M only, it would be 73 over 173. If it was probability of M only. But now it is probability of M, so it generalizes now that cell M. So you're going to take the entire, well, all the complaints in that cycle M, because it's about M, not only M.
Okay.
So it will be 73 plus 20 plus 6 plus 11 divided by 173 plus, what is probability of F?
55.
55.
20. I want your thinking process.
Oh, sorry.
20 plus 13 plus
13
6 plus 16
plus 16 over 173 minus. Now I will give you a reason why we say minus, but let us write down this probability of M and F. What is that one? What is that one? What that one?
Oh, it was 26, I think.
26 over
26 over
173.
175. Yeah. 173. So.
Probability of M and F, you will check the intersection of M with F. That is 20 and 6, 20 and 6. So that will be 26. Then that will be 20 plus 6 divided by 173. And then you press that on your calculator. What do you get?
$139 over 173.
139 over 173.
Yes, so I get.
Okay. Let me give you the reason why we subtract.
No, it is.
Eh?
Let me recalculate. Yeah, it's right.
Say it's similar to yours.
Why are you doubting me?
Eh? It's better to say it's similar to yours.
Okay.
Yeah. To say it's right, it's a very completely different discussion.
Yes. Is it 139?
Who else got
It's
who
similar
got
to
another?
mine.
Sorry?
139 over 176, 173.
139 over?
173.
So it's similar to yours as well. Or is it correct?
No, it's similar.
Oh, okay. No, because similarity does not imply being correct. We can have 10 people with similar answers, but that does not imply that they are correct.
Correct.
Yeah. If you get to university and start studying mathematics and the logic, you will get that understanding and the logic. So yeah, I think we have been at it for a very long time. Yes. I think let's move to another question. No, it's close to 9. I think we should close.
Oh, thank you so much, sir.
So,
yeah, I think we should close.
When do we meet again?
Yes.
Never.
Never.
No, we're meeting Saturday, same time for paper 2.
Can we not do paper 2 tomorrow?
Mr.
So can you add someone in the group, please?
Sorry?
Can you add someone on the group? I'll send you their number.
Can I add something?
Someone on the group.
Can I add who?
Add someone on the group.
Oh, okay. No, it's fine. I will add someone. You can just text me. I will then add that someone. Otherwise,
yeah, I'll add you.
You wanted to say something?
No, we're just saying thank you.
Nango.
Thank you.
Yeah,
Thank you.
You can go attend Abu Zizi.
Okay, guys. No, it was a lovely interactive lesson.
Thank you.
Hopefully, we keep the same energy for Saturday, same time. Make sure that you nail that paper 1 and you come to paper 2. All the best.
Thank you.
Sure.
Double. Thank. Bye-bye.
Very nice.